Hey guys, this is Yash Khanolkar and today I'm going to demonstrate DLIC experiment 2, which is on the application of op-amps using the adder subtractor and the linear equation circuit. Now the last time I already showed how to use the LT-Spice software, so today we will jump right into the demonstration. The first circuit which I will be demonstrating is the subtractor circuit. As you might have guessed, in the subtractor circuit, the output voltage is the difference between the input voltages. So V out here is the difference between VA minus VB. And in this circuit, we use four resistors. The feedback resistors R5, R3, and R4 as the input resistors, while R1 is the bias compensation resistor. VA and VB are the input voltages, and VEE and VCC are the supply voltages. Now we need R5 by R4 ratio to be 1 because we want the coefficient of VA to be 1 so that the circuit can act as a subtractor. Now in the output we want VB to be negative, so we connect VB to the inverting terminal of the op amp so that VB is negative in the output, and VA should be VA at the output, so we connect it to the non-inverting terminal. So we can just then run the circuit and we can see the operating point values here. So just click cross here and you can see the values. Now you can obviously check that VA minus VB, you have taken VA as 5, you have taken VB as 1. So VA minus VB, 5 minus 1 is 4, and our answer is pretty close to that answer. So the simulation is by and large correct. Now we can also do this simulation with the help of other op-amps like LM741, like TL081, and the only thing you have to change is you have to add the DC voltages, the DC offset voltage here. So in this case, if we take the offset voltage as 0.001, so then this will be 1.001 and this will be 5.001. And if you take the offset voltage for each of the op amps, then you will see a slight difference in the output value of the op amp. Now there's one more thing which you can do, and that is you can change the value of the resistors. If you change the value of the resistors, one thing which can be seen is that the voltage of output and input remain constant while the input and output current decreases. So we can find the power and the power at input and output and the power dissipated between input and output. So this is all we can say for the subtractor circuit, and after that we go to the non-inverting adder circuit. Now for the non-inverting adder circuit, the adder circuit means that we have to have the output voltage as the sum of the input voltages, and non as it is a non-inverting adder circuit, then we have the sources at the non-inverting terminals. Now we have taken here values of 2 volt, 3 volt, and 4 volt. We can even change these values. You can extend it with 1 volt, 1 volt, 1 volt, or 2 volt, 1 volt, 2 volt, whatever you want. And we have to have the coefficient of all three as 1, so we have taken the same value of resistors for R6 and R1, R2, and R3, which we have taken here as 10k. Now I have taken here the inverting resistors as 4.7k and 330 ohms. So that's because we want a standard value of the resistance, so we have to take the resistance as close to 5k as possible. So we then just run the circuit. So you can see the operating point here, and you can see that the addition we get is 9 volt and we are getting at 8.96 volts, so that's okay. So this also you can have do the same thing as the subtractor circuit for the other op amps LM741 TL081, and you can change the resistor values and see what happens. And this is what you do for non-inverting adder circuit. Now the next circuit we will be seeing is the linear equation circuit. So this circuit is a little bit different because it contains two op amps, and as you can see that we have been given equation here, so using this equation we can design this circuit. Now we have taken VA and VB for at the inverting terminal of the first op amp, and VC at the inverting terminal of the second op amp, and you can see here the coefficient of VA is 2, so the R4 by R5 plus R7 the value should be 2. So we have here R4 as 10k and you have this as 5k, so 10k by 5k is 2. Similarly we have the coefficient of VB as 3, and we have here the value of R6 as 3.3. So 10 by 3.3 is approximately 3. And as we can see, we have taken VA and VB as a 1 volt. You can take anything. So by the formula, we can see that we have 2 VA and 3 VB here. And because we have connected to the inverting terminal, then the 2 VA and 3 VB will be minus 2 VA minus 3 VB, which if we put 1 as the voltage, we can get the output as minus 5. So we get V0 here as VO here as minus 5. So we give VO as the input to the inverting terminal along with VC, where VC is 1 volt here, but the coefficient of VC is 4, and so we have to take R as 10k, and here we have taken R2 as 2.55k, to 10 by 2.55 is almost 4. So here we have 4 VC. The 4 VC after connected to the inverting terminal will be minus 4 VC, and this is already minus, which again after inverting will turn into plus. So we get 2 VA plus 3 VB minus 4 VC according to the formula. Now we will just run this circuit. So we can see that the answer is almost 1.078, and which is very close to our answer. So the circuit is running perfectly. Now this circuit also you can do the same as in the previous two circuits. You can check with LM741, you can check with TL081, you can make the modifications, you can give the DC voltages, and you can find the values. So that's it for the video, guys, and I hope you like the video, and thanks for watching the video. Thank you.